Chapter 8 covers acids and bases. So in this chapter we will discuss here, as shown in this overhead, we will cover common examples of acids and bases. We will cover chemical definitions of acids and bases. Then we will examine acid and base reactions. Of course, as you can imagine, being a chemistry class, we'll have to cover some reactions. We have a new term here that we'll define, and that is conjugate acids and bases. So we'll define that term, and then we'll apply that term or that concept to reactions of acids and bases. And lastly, in this lecture, we will look at the relative strengths of acids and bases. Okay, so let's start our lecture. We're very familiar with acids and bases. We just have to look around our environment, such as the kitchen. We can see vinegar and dishwashing liquid and different types of reagents around, and we often describe them as acids or bases. The general definition of acids is that it has a tangy taste, and bases, they have a slimy feel. But of course, as you know, as chemists, we cannot go around tasting chemicals to determine if they are acids or bases or feeling chemicals. So let us look at a chemical definition of an acid and a chemical definition of a base. And this definition came in the 1800s, over 100 years ago, by Arrhenius. So remember that name, Arrhenius' definition. What he basically stated was that an acid is a substance that produces a proton. Okay, so we are defining here a proton as H+. Pay special attention to that representation, H+. It is a hydrogen without electrons. We call it a proton. So Arrhenius defined an acid as a substance that produces H+, hydrogen plus. We call it a proton. We know that a proton, it's very reactive, so it reacts immediately with water to produce a new intermediate or a new type of molecule or intermediate called a hydronium ion. A new type of ion called a hydronium ion. Of course, why water? Of course, as you know, water is the most common solvent, so that's why most definitions are referenced to water. So the proton here, notice again, H+, you'll see this a lot throughout this lecture and throughout this chapter. H+, the proton in water forms a ion called the hydronium ion. So that's one example of the reaction of the proton in water to produce the hydronium ion. But the bottom line is, the definition of an acid is a substance that produces H+, or another term for H+ is proton. A base, on the other hand, he defined a base as any substance that produces here the hydroxide ion or the OH ion. Notice it has to be in aqueous solution in water to produce OH minus. So we'll broaden that definition before too long, because we have reactions that take place in other solvents. But as a starting point, the base is any substance that when mixed with water produces the OH negative ions. So here's an example, or here's an application of that concept. So once again, my approach is for us to know concepts, and equally important is the application of that concept. As scientists, that's what we do a lot of, is applying our understanding to solving problems. So let us imagine here hydrochloric acid, HCl. We know that's a strong acid, and we know it dissolves completely in water. So what does that look like? So if you were able to get inside a beaker and you looked around and there were HCl and water present, what would you see? What you would see is that water as a solvent is present. We have HCl as the reactant is present. But after the reaction occurs, we also find this here as the hydronium ion again. And we also will find Cl minus, the chloride anion, in water. Notice AQ here just means that it's solvated because we have a large concentration of water around. So this is the reaction of hydrochloric acid in water. Another way of representing what I just described is, here is water again, and of course, as we know, that is the Lewis dot structure of water. Here are the non-bonding electrons. Here are the bonds to hydrogen. So this is water, H2O, same as here, but just now drawn out. And here is hydrochloric acid, HCl, just now drawn out as H bonded to Cl. What happens for a reaction? We often use this representation here, arrows, to indicate electron movement to form bonds and to break bonds. So here's an arrow showing that these electrons are bonding to this hydrogen to form this hydronium ion. So these electrons here are now right here. In the process, it took here that hydrogen. So here's that hydrogen. And we have here the chlorine coming off as Cl minus. Notice these electrons here are now right here. So they've taken those electrons. The bottom line is, you may recall that this is a polar covalent bond, where this is partially positive and the Cl is partially negative because it's electronegative. So if this bond is broken, the Cl will take these electrons over here, leaving behind H without its electrons, and H without its electrons is a proton, as we have defined. So the bottom line is that this is an acid because in the reaction it has given up H plus to water to form here the hydronium ion and Cl minus. So HCl, based on the definition of Arrhenius, is an acid because it has given up its H to another molecule. Let's look at the definition of a base. Much easier concept here because most bases that we will discuss in this lecture is bonded to a metal to the extreme left of the periodic table, such as sodium, potassium, magnesium, and calcium. But notice, since it's a molecule, an ionic molecule, since it's bonded to OH negative, this is the base because we have here the OH. We have this is a base, so you can easily recognize a base because of the OH that's present. So here's an example. We take this molecule Let's assume we do not know what it is, if it's a base or an acid. You add it to water. You get inside and you look around. What you'll see after water has been added is Na plus, because that will be broken up into the ions, and OH minus in the presence of water. Because it has produced OH minus hydroxide ion, this molecule here is a base. Here's another application. Not all molecules, as we mentioned earlier, will have the OH present to indicate that it is a base. It is possible to have molecules that do not have the OH present and they're still base. So let's look at this molecule, ammonia, NH3. Is that a base or an acid? So we put this in water. After you put this in water, what you get is NH4 plus and OH negative. That's what's really happened. This NH3 is now converted to NH4. Notice 4. So it has acquired one H. Remember, by definition, if it has here NH3 and more H's over here, it is a different molecule. The other aspect here is that this is water, and water will react here to give up that H. So here's that H that's given up from water. So what's left behind is OH negative, which is the hydroxide ion. So therefore, this is described as a base, NH3. The next slide has a better illustration of this concept. So let us imagine again, we have this NH3 drawn out as the lowest structure. Here, a pair of electrons. Remember, it's two dots represent an unshaped pair of electrons. These unshaped pair of electrons can now bond to this hydrogen, which is partially positive because this bond here is a polar covalent bond. You will recall from previous chapter that water is a polar molecule and the OH bonds are polar covalent bonds, which means that this hydrogen is partially positive and this oxygen is partially negative. So if this bond were to break, it would take these electrons here, because here they are, it's electronegative. If this bond were to break, this hydrogen would go to this nitrogen with the electrons, and here it is. So once again, this molecule here is a base, because if mixed in water, here is water, it produces here the hydroxide ion. So you should be able to look at a molecule and say if it's dissolved in water, will it be an acid or will it be a base based on the definition of Arrhenius? Let us turn our attention now to strong acids and strong bases. A strong acid is one that completely dissolves. In other words, if you take HCl and put it in water, you will not see any HCl molecules, but you will see Cl minus and H3O plus. So that's a strong acid. So we'll have to tell you what a strong acid is. So here's a strong acid, HCl, here's another strong acid. So that information will be given. So if that information is given, you can tell that it will dissociate 100% or almost in water to give the ions. Same for the base. A strong base will dissolve in water to give the OH negative anion, hydroxide ions. But you will be told in the next part of this lecture, or the last part of this chapter, you will see how to calculate the equilibrium constant, and based on that, the magnitude of the equilibrium constant, you can tell if an acid is a strong acid or a weak acid. A weak acid is only partially dissolved in solution, in water, because our solvent is water for the time being. So acetic acid is an acid that's only partially dissolved in water. So that information must be given to you. You would not know that. So therefore, it is a weak acid. So what that means is, if you take acetic acid, which is right here, and dissolve it in water, and if you should look around that beaker, what you will see is the acetate anion, or the anion that results after the removal of the proton, because it's an acid, and you will see the hydronium ion, which means that this water took this proton. So what you'll see in solution is a mixture of all four: two reactant molecules, including water as a solvent, and you'll also see two product molecules here, and the hydronium ion. That means it's not completely dissolved. Let's see, what about a base? You take a base, for example, NH3, and you mix it in water, and what you'll get is, as we have seen before, it's NH4, where one of these hydrogen goes over here to that ammonia to get OH negative, the hydroxide anion, and NH4. So again, it's only partially dissolved, it's weak, so that information will be given to you. So if you were to look around that beaker, what you will see would be all four of these. But because it is weak, we have a lot of the reactant molecules here compared to the product molecules. Just like here with acetic acid, because acetic acid is weak, you'll have a lot of acetic acid molecules compared to the dissolved species. So that means it's a weak acid and a weak base. Let us look at another definition. Of course, as you can imagine by now, in chemistry, way back in the 1800s, we had Arrhenius developing that definition for acids and bases. As time progresses, other chemists came along, and they developed definitions that are much better in describing new discoveries. So this is a definition from Bronsted and Lowry, two chemists. So we call it the Bronsted-Lowry definition of acids and bases. So don't forget those names. In chemistry, we like to associate names with different discoveries. So what Bronsted-Lowry discovered was that a Bronsted-Lowry acid is a proton donor. Essentially the same definition as Arrhenius. But a base is a proton acceptor. So a base will accept a proton. So this is a slightly different definition. So let's make sure we understand this definition, because we'll ask you to apply this definition. So an acid is a proton or H plus donor. So you'd expect an acid to give up H. So in other words, an acid must have here an H to give up. A base accepts that H. So for example, a Bronsted-Lowry acid is HCl, as we know is an acid, since it gives up H plus to water. As we have seen before, here is water, H2O, here is HCl, this is the hydrogen, but now this hydrogen here is bonded to this water. So in going from reactants to product, HCl gave up its hydrogen to become the hydronium ion. Therefore, it is an acid based on the Bronsted-Lowry definition of an acid. H2O is described as a base because here is H2O and it went to H3O plus 1, 2, and 3 hydrogen. It has acquired another hydrogen, so therefore it is a proton acceptor. So based on Bronsted-Lowry definition, water here is a base. So these are chemical definitions of acids and bases. So in chemistry, you do not go around tasting chemicals to see if it has a sour taste to make a decision if it's an acid or a base. You do not go around feeling chemicals to see if it's slimy to determine if it's a base or not. We apply these definitions to solving problems, in this case to determine if a molecule as written is an acid or a base. Let us look at another concept here, and this one we'll call conjugate acid-base pairs, or acids and bases. So in this case, we're looking at the same reaction, but now we will concentrate on the product. So here is a reaction. Here are the reactant, 1 reactant, 2 reactant. When they are mixed, what we get is a product, an anion, and a product, a cation. So these are the products. So we'll concentrate now on the products. So let us look again at the reaction. Acetic acid, as you know, is an acid because in going from reactant to product, it gave up a hydrogen. So it's a proton donor, it's an acid. The same acetic acid converts to an ion called the acetate anion. Here, the only difference between the acetate anion, the product, and the acetic acid, the reactant, is that the hydrogen is gone. So this species over here is called the conjugate base of acetic acid. So the conjugate base of acetic acid is the base that results after the loss of a proton as a conjugate base. Let's look at the other reactant, ammonia. Here is ammonia, NH3. In the product, it's NH4. The difference between NH3 reactant and NH4 product is that the product has an extra hydrogen, so it has acquired a hydrogen to make the product, and the difference is ammonia, the base, is transformed to ammonium ion, and this is called the conjugate acid of ammonia. Why is it called an acid? Because if you were to look at the reaction in the reverse direction, it loses the H to form H3. But we'll get there. So it's an equilibrium reaction here. But the bottom line is that you should be able to look at an acid and determine its conjugate base. You should be able to look at a base and determine its conjugate acid. The only difference is a proton. So conjugate acid-base pair of any molecule is just an interconversion based on a transfer of a proton. So you should be able to look at a molecule, determine if it's an acid, based on the Bronsted-Lowry definition or the Arrhenius definition, and you should be able to determine what is its conjugate base. Same for a base, determine what is the structure of the conjugate acid. Let us look at a more detailed application of this. So here is acetic acid. Here is the proton or the hydrogen. Because this bond is polar, this is your partial positive. And of course this oxygen here is your partial negative. So this hydrogen here is considered partially positive, or if it reacts, it will react with electrons. Here are 2 electrons, so these 2 electrons will take this hydrogen and bond here. Here's that bond, and acquire this hydrogen. Here it is. So this NH3, which is a base, has acquired a proton, a hydrogen, to become NH4. So therefore this is the conjugate acid. The acetic acid has the proton in the reactant, but in the product the proton is gone. So therefore this is described as the conjugate base. So once again, the only difference between a conjugate acid and a conjugate base is a proton that's removed from the conjugate acid and goes onto the conjugate, a proton that's removed from the acid to form the conjugate base. So let me repeat. So the only difference between an acid and its conjugate base is that the acid has lost a hydrogen to form the conjugate base. Let us apply that to a possible question that you may see on the quiz or on the test exam. So the question is, which of the following is the conjugate base of water? So this is we need to determine the conjugate base. So in other words, which means that now we have water HOH. To determine if it's a conjugate base, to determine the conjugate base, we need to remove a hydrogen, because by definition a base is a proton or hydrogen donor. No, a base is a hydrogen acceptor. So, but in this case, it will be acting as an acid. So what is the conjugate base? So here we have H2O. If we remove this hydrogen, we have a conjugate base. So let me repeat that, because I made an error earlier. So once again, what is a conjugate base? Which means that what is the acid? The acid here would have to be water, which is this. To determine the conjugate base, we'll have to remove H. So what's left behind is the conjugate base. So, possible choices. Could it be H3O plus? Probably not, because H3O plus means that H2O has acquired a proton. If it acquires a proton, it becomes a conjugate acid. Could it be NaOH? Possibly not, because we do not have sodium hydroxide in. Could it be OH negative? A good answer, because if you take H2O and remove this, what's left behind is that. Could it be O2 negative? No, because to get the conjugate base, it's just the removal of the 1H from the acid. So let's see what's the answer. The answer, of course, is, as you might have guessed, is OH minus, because here The acid here is H2O, and to get the conjugate base, we simply remove this hydrogen, which means that what's left behind is OH negative, OH with its electrons, which is that. So you will be asked on the quiz and on the test to identify conjugate acids and conjugate bases given an acid or a base. Let us take this further. Acids can be positively charged, can be neutral, or negatively charged. The main thing here, though, is that all acids must have at least one hydrogen. Because by definition, remember Bronsted-Lowry definition is an acid is a proton donor. So let us look at one that's positively charged, H3O plus. Here's a positive charge. If you react H3O plus with water, it gives up one of these hydrogens to water to form H3O plus again, but here is water. So this is an acid that's positively charged. Let's look at an acid that's neutral, carbonic acid, H2CO3, neutral. Put that in water. One of these H's will go to form this. By the way, one of these H's should be red. And since it has lost one H, what's left behind is HCO3 negative. So this is an acid that's neutral. Let's look at an acid that has a negative charge. This is the phosphate anion. Notice H2PO4. This is H2, but it has a negative charge. React this with water. This H3O plus, again, one of these H's should be red. So let me write this out. So this should be another H here. That's red, and this should be 2. So one of these H's here will go to this oxygen, and here it is. And this acid has now gone to HPO3 negative 2 and lost one hydrogen, because by definition an acid is a proton donor. So here's the acid giving up one proton to the base to form the conjugate base over here. Conclusion. So acids can be positively charged, as we have here. Acids can be neutral, as we have here with carbonic acid, or acids can be negatively charged, as we have here with that negatively charged phosphate anion. So let us look here at classifications of acids. So conclusion. Acids can be monoprotic, as you can imagine. Mono here means one. HCl is a classic example. One hydrogen. Acids can be diprotic. Di here means two. And here's an example, H2. Remember that protic here is just another term for hydrogen. It's actually H plus. And of course, here we have an acid can be triprotic, 3 protons. So that's triprotic acids. So look out for that. You may be asked to classify an acid as monoprotic, diprotic, or triprotic. Okay. Let us look here at carbonic acid again. So here we have H2CO3. As we have seen before, this is a neutral molecule which is diprotic. Reacting with water, it gives up one of these hydrogens to form H3O plus from water. And what's left behind is the conjugate base, as you'd expect. Here it is. Bottom line is that this diprotic acid gives up a proton. This intermediate here is also acidic because it has a hydrogen. So let's look at that reaction with water. So this is a hydrogen. It can give it up to water over here. So you can take it to form another mole of H3O plus. And what's left behind is this anion, which is now the conjugate base of this acid. So it sounds a little confusing, but if you have a systematic approach to solving these problems, and the systematic approach is to get back to the concept, the definition, an acid is a proton donor. So here's an acid with a hydrogen. If it, in going from reactant to product, if it gives up this hydrogen or lost it, it's an acid. After losing that hydrogen, what's created here is the conjugate base. Okay, let's look at another concept here. A base can be negatively charged. So here's your base. Well, let's assume you do not know that yet. So here's OH negative. You're not quite sure if it's a base or an acid. In the presence of HCl, you know this is a polar covalent bond, partially positive and partially negative here. So this is acting almost like a proton. In going from reactants to product, notice the OH here goes to H2O, acquires one extra hydrogen. So it's a proton acceptor. So therefore this is a base. This is an acid because in going from reactant to product, it has lost a hydrogen. So that is an acid because it has given up a hydrogen, this hydrogen, in going from reactant to product. Same here. Ammonia is a reactant. It gains a hydrogen to become NH4, the conjugate acid. Therefore, this is a base, and this is the conjugate acid. HCl, in going from reactant to product, it has lost this H, so therefore it is a proton or hydrogen donor. So therefore it is an acid. Since it has lost a hydrogen in going to the product, this is called the conjugate base. Okay, let us look here at another example. And this is the base, carbonate, reacting with an acid. But let's just assume we do not know that it's a base or an acid. Let's assume you're trying to determine if it's a base or is this an acid. Let's examine the reaction based on our definition of acids and bases. Here's a reactant, and the reactant went to this. So it has one hydrogen here. Over here it has two. So it has picked up, or it is a hydrogen proton acceptor. Therefore this is the base, and this is the conjugate acid of this base. Here's HCl. So examine the reaction. HCl as a reactant goes to Cl minus. In so doing, it has lost this H. So therefore it is a proton, hydrogen. It's donating its proton or hydrogen. So therefore it's an acid based on the Bronsted-Lowry definition. An acid is a proton donor. So HCl, in going from reactant to product, has given up its hydrogen. So this is the acid, and this is the conjugate base because it has lost its hydrogen. So you should be able to look at any acid or base and determine the conjugate base, conjugate acid or the conjugate base. Same here. Let's assume you do not know what this is, but it is, by close examination, it has an H over here in the reactant, and going over here, notice no H. It has lost its hydrogen. By definition, a species that give up a hydrogen or loses a hydrogen is an acid. In going to the product, after it has lost its hydrogen, it's called a conjugate base. Let's look at this one. OH negative. It goes from OH negative to H2O. So OH negative has gained a hydrogen. So this is a base, and this is its conjugate acid, because by definition a base is a proton or hydrogen acceptor. So in going from reactant to product, it has accepted an electron. Therefore this is a base and this is its conjugate acid. You may be wondering what happened to the sodium, but the sodium is an ion, cation, so it balances out this anion. So once again, you should be able to identify acids and bases, and also conjugate acids and conjugate bases, because we'll use this concept in the next later on in this lecture. So as a summary for this part of the lecture, you can have an acid or a base that's described as a substance that can either act as an acid or a base. That's called amphiprotic, as we saw with the carbonate, because it can give up a proton and it can accept a proton. That's amphi. Amphi here means many, and of course you can recognize the protic here means protons or hydrogen. Another example is water. Water is amphiprotic because, as you know, it can accept a proton to become H3O plus, hydronium ion, or it can lose a hydrogen to become OH negative, which of course, as you know, is the hydroxide anion. Let us look here at the Bronsted-Lowry definition of acids and bases again, and let's do a close examination. We have described acetic acid as an acid, and if you notice, acetic acid has CH3 and COOH, so it has one hydrogen and three here, so it has three hydrogens. We defined an acid as a substance that has hydrogen, and we defined an acid-base reaction as the proton or the hydrogen donation. The question now is, could this be acidic? Is this acidic? Is this acidic? Or is this the one that's acidic? You'll have to resort to a concept that we did before, where we have here a polar covalent bond to the hydrogen, bonded to very electronegative oxygen. So therefore this hydrogen here is partially positive because these electrons here are closer to the oxygen than the hydrogen. A similar situation would not exist over here because carbon is not as electronegative as oxygen. So look at the periodic table. Carbon is to the left of oxygen on the periodic table. Thus this bond here is not as polar. In fact, it's not polar compared to this OH bond. So this hydrogen here is the acidic bond, hydrogen. So in analyzing a molecule that has more than one hydrogen, the hydrogen that's bonded to the most electronegative atom is the acidic hydrogen and will be the hydrogen that's donated in an acid-base reaction. Let us look now at the strengths of acids and bases. So we have a strong acid, we have weak acids. Of course, as you know, hydrochloric acid is a strong acid and acetic acid is a weak acid. Now we'll try to figure out why. Here is acetic acid, vinegar, weak acid, and of course we have a strong base here, such as sodium hydroxide. So let us use chemistry now to determine strong acids and weak acids. Here is the concept that we'll rely on. Strong acids have weak conjugate bases. So the stronger the acid will be the weaker the conjugate base. So now you can see the importance of identifying conjugate acid-base pairs. You can see the importance here of identifying an acid and identifying its conjugate base. If its conjugate base is weak, it's a strong acid. If this acid is very strong, its conjugate base will be very weak, just based on this statement here that's known in chemistry. For example, HI is an extremely strong acid. So this information we'll have to give you. Later on we'll see how to determine that information based on the equilibrium constant. But for the time being, I'll tell you that HI is a strong acid, which means that its conjugate base is a weak base. Its conjugate base is, of course, I minus, which would be HI without the hydrogen. Because it's an acid, it will donate the H. So this is the conjugate base. It is a very weak base. Same with HCl. HCl is a very strong acid. So let's put HCl here because that's a very practical example. HCl is a very strong acid, but this conjugate base of HCl is Cl minus. It's a very weak base. Of course we know that because sodium chloride, which is NaCl, this is Na plus and Cl minus, we do have NaCl minus in table salt, and of course we know that's not a very strong base. It's a very weak base. Acetic acid is a stronger base than carbonic acid. So this CH3, COOH is stronger than this one. So what does that say? The conjugate base of acetic acid is weaker than the conjugate base of carbonic acid. So again, you can see the relativity of the strengths of conjugate bases. So if you have a very strong acid and a very weak acid, the strong acid will have a weak conjugate base and the weak acid will have a strong conjugate base. Okay? So let's look at this again. So HCl, we know it's a strong acid, and if mixed with water, will give us Cl minus and H3O plus. As you may recall, this is the conjugate base of HCl, and this is the conjugate acid of H2O. Since it's a strong acid, the equilibrium is all the way over here, so this is a weak conjugate base of HCl. And as I mentioned in the previous slide, it's such a weak base that we actually ingest Cl minus as sodium chloride, table salt. In contrast, however, as we have seen, acetic acid is a weak acid. But the question now becomes, if you mix acetic acid in water and you mix HCl in water, what happens? Because HCl is a strong acid, the equilibrium will be all the way to the right. So after you've mixed it, you will only get this in solution and not HCl molecules. If you mix a weak acid in water, such as acetic acid, and you look at what's in solution, you will see that you'll still have some acetic acid that's undissociated as in complete molecules, and you'll have the acetate anion and H3O+, which means that you have a mixture of all four in water for weak acid, but in a strong acid you'll just have the products. Now what happens if you should carry out this reaction and it's not in water? So here's an example. Acetic acid is mixed with ammonia. The product, of course, as we know, is the acetate anion and NH4. But this equilibrium, is it more to the right or is it more to the left? So in other words, will it behave like this one, where you only have the products, more to the right, or will it behave like this one, where you have a mixture of all four in solution? The question now is, how can we tell? Here's how we can tell. So we have here acetic acid and its conjugate base. So that's called the conjugate acid-base pair. Next we have ammonia. We know that's the base. And this is the conjugate acid of ammonia. So if acetic acid is a strong acid, a stronger acid, and ammonia is a stronger base, then on a relative scale, this equilibrium will shift towards the weaker conjugate base and the weaker conjugate acid. So in other words, the equilibrium will lie to the right on the side that has the weaker base and acid. So once again, let's look at this. So acetic acid, an acid, and ammonia, a base. We know that this is relatively strong, but this is the conjugate base, which is weak. Ammonia is a relatively strong base. This is the conjugate acid. Because it's a strong base, it gives a weak conjugate acid, weaker conjugate base. So therefore the equilibrium will lie in this direction for this reaction here. So once again, you should be able to look at a reaction, and if I were to tell you that this is a strong acid and this is a strong base, you should be able to predict the position of the equilibrium if it lies to the right or to the left. If I were to tell you that the conjugate base and the conjugate acid over here are extremely strong, then you would predict the equilibrium lying to the left. And here's an example. So what we'll do later on in this course is we will actually calculate the strengths of acid. But you can use this table for the time being. HI is a strong acid, so therefore its conjugate base I- is weak. Here is carbonic acid in the middle, not as strong, so therefore its conjugate base here is not as strong. Here's water down here, an extremely weak acid, of course, as you know, extremely weak because we ingest it every day. So it's an extremely weak acid. But its conjugate base is the OH minus, and as you can imagine, it's a very strong base. So as you can see here, this trend for the acidity is opposite for the trend of the conjugate base in terms of the strengths. So, in conclusion, let's look at this one. Predict the position of the equilibrium of this acid-base reaction. So in other words, you need to locate which ones are stronger and which one is weaker. So locate the strong acid and the strong base and figure out which side of the reaction or the equilibrium it is. So in other words, you'd have to be told or look at the table. Carbonic acid is a stronger acid than water. So look at the periodic table, you can see that carbonic acid is a stronger acid than water. The other reactant, OH minus, is a stronger base than the conjugate base of carbonic acid. So you'd have to look at this table here to make that observation. Or you will be told the equilibrium lies in the direction of the weaker acids or base. So since this is weaker, based on that table, the equilibrium here lies to the right. Conclusion: the equilibrium of an acid-base reaction lies in the direction of the weaker acid and the weaker base. And you can determine the weak acid and the weak base by knowing the structures of the conjugate acid and the conjugate acid-base pair. Okay, this is the end of this lecture for the first part of Chapter 8. So read upon this. I know this concept is new for us. It's going to take a little while before you fully understand the concept and can appreciate it, and equally important to apply it to solve these problems. So take your time reading through. You may have to pause the video at different points and read your note, the text, just to make sure you understand it. And I'll post another video shortly on the last part of Chapter 8. Okay, so look out for that. Don't forget we have a quiz next, well, not a quiz, we have our third exam next week, Thursday, which is November 19th. So get ready for that, because Chapter 8 will be on that. Okay, so continue to study hard and get ready for the exam. Okay.